All right, here we go. So we're talking about functions, we're talking about transformations. So it's really all the same stuff that we've been talking about all along in this unit. But we're getting a little more into function notation, and we're going to look a little bit at functions that aren't like typical functions. So we're kind of broadening our understanding a little bit. So this says, how are the functions y equals x and y equals x plus 4 related? And then how are their graphs related? So notice that's two different questions. The first question is, how are the functions themselves related? The second question is, how are their graphs related? So who can tell me something about that? Claudia. Okay, so these are both linear, right? These are both y equals mx plus b style equations. Will, what can you tell me? So you could say that they are parallel. I'll put that under the graphs. They're parallel functions, parallel graphs. Lucas.
Y equals x is the parent function, and y equals x plus 4 is the
Child function. Yep, this is the child to that parent. So Will got at the fact that they're parallel. That's sort of looking at it from the graphing side. Looking at it from the algebraic side, what would we say about that? Other Will. They have the same slope. That's what makes them parallel. Whoops, weird things happening. So they're both linear and they have the same slope. Okay, what makes them different? What about them is different, Lucas?
They have a different y-intercept.
They have a different y-intercept. And if we were to describe that using a transformation, what transformation happened? Claudia. So that's rotate, reflect, translation. So it translated up 4. Now this is an interesting thing that is only an ambiguity with lines. It's not an ambiguity with anything else. So I'm going to show you something that's just sort of an interesting, So the parent function would have been like this, yes? And then you guys said the transformation that took place is that it translated up 4 spaces, right? So like we think of this point moving up here 4 spaces and then they're parallel. Yes? Okay. So if I just zoom in on that part, we would say, I got to make this thinner or you won't be able to read it, that this went up 4. Yes? But I want you to think about something. How far could you think of it as having gone that way? 4 to the left. Now, this ambiguity doesn't happen with other types of functions, but it does happen with lines. Claudia?
In most other functions, it's x and then it's like a function applied on it. So you do in parentheses x plus 4, and then it shifts 4 to the left or into the negative because everything is inversely
Yeah.
and then applies the function. But here it's just y equals x plus 4. So it could either be y equals x with a y-intercept plus 4 or y equals the x value plus 4.
All right. So summarizing, Claudia is basically saying in a linear function, there's no extra thing happening to the x. But in all the other functions like cubing or square root or log or whatever the case may be, you're doing something to the x besides just like adding or subtracting, right? So when we have a linear function, in order to cause us to think about this as being a translation 4 to the left, we would just need to throw parentheses around the x plus 4. When you look at it from an algebraic perspective, those parentheses don't do anything, so we don't think about it that way. But it is a good thing to note that with a line, when you don't have additional transformations taking place, you actually can't tell whether something moved up 4 or left 4. Effectively, it'll be the same thing, right? Because the way the algebra works, the parentheses would be unnecessary. All right, so that's just a little interesting thing about lines. So we're going to take a look at number 2. What is the graph of y equals x squared reflected about the x-axis and translated down 3 units? Okay, so we're not looking at writing the equation that makes that happen. We're just looking at the graph. So I tend to like to think about a series of more basic graphs and how they build. So just show me in the air quick with your hands. What does y equals x squared look like? Yeah. So real rough thinking, this is y equals x squared, yes? Yeah, okay, so there's my parent. So if I reflect it about the x-axis, instead of using the word about, we can also use the word across. It's the same thing. So imagine taking that and reflecting it across the x-axis. Show me in the air, what would that look like? Yeah, so basically when we reflect about the x-axis, we're flipping upside down. It's now going to look like this. Everybody okay? Yes? Then it says translate it down 3 units. So after we reflect across the axis, then we're going to translate down 3 units. That won't change which way it's facing. It's just going to be like it dropped down, like it slid. So now it's going to look like that. Okay, this is then take it down 3 units. Is everybody okay with that progression? Okay, so that's in rough draft form, but we'd like to think about a few points. So I'm going to go back to the parent function. So if I imagine the parent function, x, and then we're squaring x to get the y's. If I imagine the x values 0, 1, 2, 3. If I squared those 4 x values, what would I get? Square 0. 0. Square 1. Square 1. 1. Square 2. Square 3. 9. Okay. So without any stretches or compresses, this is the relationship between the points on the curve. Okay? So here's how I graph something like this. I don't actually do any more calculation than that. I've already thought through the rough draft of basically what it looks like. So I'm like, all right, I can put my x-axis up pretty high because none of my graph is going to be above the x-axis. I can keep the y-axis in the middle because this didn't slide to the left or to the right. So I've thought about axis placement. Okay? And I can do that because I already have a sense in my mind of basically what it should look like. And then I'm like, okay, normally that like 0, 0 point would be at the origin. But see how our like point that used to be 0, 0, it's now down 3 spaces from where it used to be? So my vertex of my parabola is going to be this point right here. So the point 0, -3. That's from the downward slide. Are we okay? Yes, we're good? Fill out a pass. All right. So we're at 0, -3. Now, I need to think about the relationship between the points. And because I am tethered to my computer today, I can't go point at the screen. So we're just going to have to work on this. So see how the first point is 0, 0, and then the next point is 1, 1? So normally that would be 1 to the right and 1 up from my origin. Is everybody with me there? Okay. Now, are we going up? No, we're going down, right? So now it would be 1 to the right and 1 down. So I go to this vertex point and I go 1 to the right and 1 down from where that is. Does everybody see what I'm talking about? But we know that parabolas are symmetric. So if I can go 1 to the right and 1 down, I can also go 1 to the left and 1 down. How are we doing so far? We okay? All right, now, here's the deal. I always have to reference the original point on my graph. So see how the next point says go 2 to the right and 4 down? That's 2 to the right and 4 down from the vertex, not from the last point I graphed. So I go back to my vertex, which should have been at the origin if it hadn't moved, and I would go 2 to the right and 4 down, and then I would also have that mirrored point. And if I have space on my graph, I can go back to the origin, the vertex, and go 3 to the right and 9 down, which I don't quite think I have space for. The bottom of the line would have done it?
Yeah.
Oh, that's a bad side of the graph. Let me make that a better curve. There we go. So the point of this is not to have to label a whole ton of points. The point is to understand how the shifts are taking place. So I'm just going to leave my labels there for now. Once we get into the quadratics unit, you will be labeling a lot more than that. But for right now, that's all I need for reference. Are there any questions about how we approach number 2? We're good? All right, let's look at number 3. Now, number 3 is them attempting to give you an application. Except the problem is their application is pretty contrived. Because realistically, the algebraic transformations they want you to do would mean you were just doing a completely different hike. But we're going to suspend our disbelief for a minute and play along with their little game, okay? And I'll tell you a frame of reference that we can use to at least make it make some sense. So first of all, let's just wrap our heads around what they're talking about. It says the graph shows the distance, f of x, you will hike if you leave at 8 a.m., okay? So notice like this point over here in the bottom left corner of the graph, like the origin of the graph, that's times 0. right? No time has passed. We haven't left base camp yet. Everybody good? Okay. So then 2 represents 2 hours after 8 a.m. So we've been hiking for 2 hours. We are now here 3 miles from where we started. Does that make sense? Yes or no? Yes? And we're hiking fairly quickly for the first 2 hours. Yeah? Okay. All right, so then we see 2 more hours passes. We get to 4 hours after we left. We didn't walk as fast. We were tired, or it was steep. We don't know, but we slowed way down. Does everybody see that? And then we picked up our pace again. We're kind of walking again at about the same pace that we were at the beginning. It doesn't really, we're not exactly sure, like, is that the end? Like, what happened? But it looked like we stopped hiking after about 6 hours. Everybody good? Yeah? Okay. So that's what's going on in the base of the fundamental graph. It says, now, what if we leave at 10 a.m.? Okay, now realistically, if you were planning on leaving at 8, but then you left at 10, are you probably going to do the same hike? No. Probably not, right? Because depending on the time of year, like you might have daylight issues or whatever. They're presuming that whether we leave at 8 or we leave at 10, we do exactly the same hike. Okay, so maybe we're hiking in Alaska and it stays light until like midnight. So we still have plenty of daylight hours to hike in. Does that make sense? Yes, I can say this because I have hiked in Alaska and it was like 10 o'clock at night. My husband and I were like, let's go for a hike. And it was perfectly light out. So we went for a hike at 10 o'clock at night. It depends where you are in Alaska. We were in the southern part. We were in Juneau. So it did get dark even in like July, but like not until like 2 o'clock in the morning. So. Not necessarily in the summer, no. In the winter, yes, but in the summer, not so much.
Alaska in the winter is just like dark all the time.
Here we go. All right, so presuming that we do exactly the same hike starting at 10 a.m. versus starting at 8 a.m., if we look at the picture, so we'd be starting 2 hours after 8 a.m. But then we're doing the same hike. So we'd be here, and then we'd be here, and then we'd go up at that same angle. Does that make sense when we look at the picture? Yes? So how did that graph move? This new graph versus the original graph. Lucas, what would you say?
What was the word you used? It was translated. It translated 2 to the right.
Yeah, we translated 2 to the right. Okay. So this is a translation 2 to the right. Okay, so using our function notation, that means we're doing f of x minus 2. Because remember, function horizontal translations are always the opposite of what you think they're going to be. Are we okay? Yes or no?
Yes, we are okay.
Yes, we are okay. Thank you. I appreciate the feedback. It is very helpful. All right, next. Now they're really going into a place where we have to suspend our disbelief greatly because they say, if you started a camp that is 5 miles into the woods, what transformation represents your distance? Okay, now if you have ever hiked before, if you hike 5 miles into the woods, can you possibly do exactly the same hike that you would have done from where you were before? No. Not on any actual mountain, right? So here's what we have to imagine. We have to imagine that the mountain happens to be a body of revolution. So maybe this is my mountain. Maybe it has like, I don't know. Come on, I don't want that. Here we go. So here's my mountain. It is what we call a body of revolution. So I imagine taking this profile and spinning it around the y-axis. So it's kind of like a cone, except a cone that got attacked on a pottery wheel. Is everybody with me? So your mountain was made on a pottery wheel. Yeah? You got the idea? I know this is very silly. I'm telling you it. Yes. Are we good? Okay. So if when I hike 5 miles into the woods, I hike 5 miles around the base of this mountain, I can theoretically now do exactly the same hike I would have done before because this mountain looks the same from everywhere. So we have to suspend our disbelief to imagine that this is what our mountain is like, and that's exactly where we hiked our 5 miles. I'm telling you, it's a contrived problem, but this would be what they had in mind. Everybody okay? All right. So if we go back to our graph around this very unusual and unrealistic mountain, now instead of starting at the origin, I'm starting 5 miles from the origin, right? 5 miles up. So then I'm going to do exactly the same graph I did before, which doesn't even fit on this paper, but it would kind of look like this. Y'all with me? Yes, Mrs. Leonard, I'm okay with this very strange problem? Awesome. Okay. So this is still a translation, isn't it?
Yes.
But it's a translation where?
Outside the parentheses.
Vertically.
Vertical translation. So how many spaces?
5.
5 up. Okay. So if it goes up and down, it's not going to happen inside the parentheses, right? So I'm going to take f of x, and to the output, I'm going to add 5. That would be expressing this using function notation. So super contrived problem, but they're trying to give you a nice application. We'll give them points for trying.
I mean, I don't think you really have to say that the mountain looks like that, because they
No.
don't really talk about slope.
It doesn't. It's more about like how much time or how much distance are you covering over time. So arguably you could cover that same amount of distance.
Yeah, I mean, okay.
Yes, I see what you're saying, Will. So theoretically we could have a different kind of mountain, but it would be hard to hike it like exactly the same speed. Yeah, you have to be purposely going at that pace. Absolutely. Lucas?
Okay, my theory is that there's actually two.
No. So in number 4, it says let g of x be the reflection of f of x equals 2x minus 7 about the x-axis. So that means across the x-axis. Everybody okay? Yes? So we have some line, and we're going to reflect it across the x-axis. So show me in the air, approximately what does the line f of x equals 2x minus 7 look like? All right. So it goes up to the right. It's pretty steep. Yes? Goes up to the right pretty steep, starting from a y-intercept of 7. Everybody good? So if I was just sketching this, it would look something like that. Totally not to scale. Y'all with me? So if I reflect this across the x-axis, it's going to look something like that. Is everybody with me on that?
I would agree.
Yeah? So the point that's on the x-axis doesn't move when I reflect across the x-axis, but everything else does. Okay, so I want to think about that. What would be g of x's equation? Will, what do you think?
Gx would be equal to negative 2x plus 7.
Yeah, so notice we could get that by taking the opposite of f of x, which would mean take the opposite like using parentheses, like distribute that negative sign. Does that make sense? So we did it visually first, but you could also accomplish it algebraically. All right. Then it says, okay, now what would be the function rule h of x if instead of reflecting across the x-axis, we reflected across the y-axis? So I'm going to have another color here. I want to think about going across the y-axis. If I do, the point that doesn't move is the one on the y-axis, and I'm going to look like that. Really rough. So what's going to be that equation? Will?
Negative 1/2 x minus 7.
I think you're working too hard.
I think that
You got the right idea, but there's an issue with your slope. Lucas?
Wouldn't it just be negative 2x minus 7?
Yes, because the idea here is I'm really just reflecting the inputs, right? My outputs are staying the same. My inputs are what's moving, right? My x values are going to be different. So if I think about that, I'm replacing x with negative x. That's what's actually happening algebraically. And when I simplify that, I get negative 2x minus 7. So if I want to reflect across the x-axis, I take the opposite of the entire function as written. Whereas if I want to reflect across the y-axis, I just take the opposite of x and then simplify my expression. Okay? All right. When we switch both the sign and take the reciprocal, that's finding a line that's perpendicular,
Yeah,
and we weren't guaranteed that we're perpendicular in this case, okay? Yes.
I understand the math and that all makes sense, but like visualizing the y-axis translation is like I can't quite visualize that.
So if I'm here, here's my axis, here's my line, and I reflect across it, I'm going to go like that,
It's like pressing your
Yeah.
face up against a mirror.
okay?
Okay, but then
It doesn't change my slope other than the sign of my slope.
yeah, that's so we did the y-axis for the first one.
Yep.
Where you called it, and then it's just translated down.
It's not translated down because, see, it's the green one and the purple
Yeah,
one.
that's
See how
what-
they have the same y-intercept? Because the y-intercept is on the y-axis.
I'm talking about the green and the red one.
The green one is not a reflection of the red one. The green one is a reflection of the purple one. The purple one is the parent function.
The red one is
Oh, okay.
There's no translation,
Cool.
just a reflection.
Sounds good.
Lucas.